This is a pretty canonical problem. It involves inclined planes, and it requires us to use our two-dimensional Newton's second law skills. And we imagine a block on a platform or some eggs on a Teflon pan in certain versions of this problem. And we're going to hold the incline at a steeper and steeper angle until the block starts to overcome static friction and accelerate down the incline. And so our task is to write an expression for the angle of the incline where it overcomes static friction and starts to slide down in terms of the coefficient of static friction. So over here is kind of what we're given. We have an incline and it's getting steeper and steeper and steeper until it's steep enough, it's at an angle theta where the gravity will overcome the force of static friction. We're given we're given the coefficient of static friction and nothing else in the problem. Here's a free body diagram of what's going on. Gravity acts down. There's a normal force that acts normal to the platform, normal to the incline, and there's a friction force that acts up the incline. Static friction always acts opposite the direction that an object would get a velocity if there were no friction. If there were no friction, the object would just accelerate down the incline. So it's a force of friction up the incline that prevents that from happening. So now I'm going to deploy this tool on it, a component diagram. And I'll tell you that I kept drawing it too small. I always draw these too small, and you may also tend to draw them too small. Draw them big, 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 so you make sure that you can have enough space to include all the features that you want. So a component diagram is like a free body diagram, except its job is, once you've identified what forces there are, now break those forces into components so you can make Newton's second law statements on them later. So here's our friend, the force of gravity. I've drawn it as a dashed line because we're going to separate into components. And I've chosen as our axes an axis that's parallel to the incline and an axis that's perpendicular to the incline. In general, we're always going to want to choose our axes in the direction that an acceleration occurs. And so when we talk about there being an acceleration down the incline, we want to choose an axis that's parallel to the incline and an axis that's perpendicular to that. So this downward dashed gravity force vector consists of a component in the parallel direction, which I've drawn in blue, and a component in the perpendicular direction, the direction perpendicular to the incline, which I've drawn in red. Is that right? If I start here and I go this blue vector, then I go this red vector, yes, I wind up at the same place as I would have if I just went down this black vector. So that force of gravity really is a vector that's equal to the sum of the parallel and the perpendicular components that I've drawn there. Note that I draw the parallel component by dropping a line from the tip of the black vector perpendicular to the parallel axis. That's how you make a projection of a vector. Okay. I drew the normal force in red because the normal force is entirely in the perpendicular direction. I drew the friction force in blue because the friction force is entirely parallel to the incline. Now I want to chase the angle theta around this diagram a little bit. Here's theta, the angle of the incline, and because this is a right triangle, I know that the complement of theta, which I label beta, is this angle here. Now I will look at this other right triangle. And because this is a right angle here, I know that the complement of beta, which is theta, is down in this corner. So I've chased theta down to here. Okay, so that's where theta lives on the component diagram. Now that we have our component diagram, we can make it algebra. Here's a statement about the parallel component of motion. The parallel acceleration comes from the combination of parallel forces acting on the mass. The parallel forces are the parallel component of gravity minus the friction force acting on the mass. They're minus because they're opposite each other. What is the parallel acceleration? Well, in the critical case where we're just overcoming static friction, it's 0. We've overcome friction so barely that we can approximate it that we've overcome it by 0. So the parallel component of gravity equals the force of friction in this case. If you were to write this as your first line, that would be fine. You'd be making reference to Newton's first law. Let me get that back up. Okay, now, substituting for FG parallel, this parallel component has a value equal to the hypotenuse times the sine of theta. The hypotenuse is the force of gravity. And on the right side, I've substituted the coefficient of friction times the normal force, because the force of friction here is the maximum static friction force that the incline can provide. We're imagining the critical case where we're just barely overcoming the maximum static friction that's available. And how much is the force of gravity? Well, it's mg. So this is an equation that we'll come back to. Now let's look at the perpendicular component of the motion. The perpendicular component of acceleration comes from the combination of perpendicular forces acting on the mass. The perpendicular forces are the normal force acting opposite the perpendicular component of gravity acting on the mass, but of course because the block is not accelerating into the incline or out of the incline, the perpendicular component is 0. So again, the normal force is balancing the perpendicular component of gravity. Substituting here, we know that the perpendicular component of gravity is equal to the whole gravity vector times the cosine of theta, because the perpendicular component is the adjacent side. So here's another equation. I've starred these two equations, and now I'll combine them, and let's see what we get. So mg sine theta equals the coefficient of friction times mg cos theta. The m and the g's cancel, which is great because I didn't know what m was in this problem. I find that the tangent of theta is equal to the coefficient of static friction. So if the coefficient of static friction is a given, then the angle at which the block will barely start to slide down the incline, the angle at which it will barely overcome the force of static friction, is equal to the inverse tangent of theta.